Let me create a somewhat random looking function, x squared minus x times y plus y squared, say. No, let's add a plus 2x in there for good measure. There's a typical looking multivariable function that in the past we have optimized and integrated. What's its gradient? It's that. We could think of that gradient vector as being a vector field. Let's go ahead and write this down. I could take that function, f of xy, what was it, x cubed minus x times y plus y squared plus 2x. And I can compute its gradient vector. It's a vector with components 3x squared minus y plus 2 and negative x plus 2y. I could plug in points into that and find particular gradient vectors, or now I could think of this as a vector field. This is a vector field. So I could graph it. I could use vector plot to graph it. And you should even know what would happen if I did that. In relationship to the contour plot of this function, we'd see vectors that are perpendicular to the level curves. That's a property that gradient vectors have. All those vectors are perpendicular to the corresponding level curve at the base, and they point in the direction in which f increases fastest, always from dark to light. Where they're more orangish, they are longer. Where they're more bluish, they are shorter. It is a vector field. We could think of it as a force field and have a curve in there. We could try to integrate this vector field over some curve. Or maybe let's do a piecewise curve that ends up being, say, a triangle. Let's start at the origin, go to the point 2, 2, go down to the point 3, 0, and go back to the origin in that direction. Call this one C1, this one C2, and this one C3. C is the overall curve. First do C1, then do C2, then do C3. It is somewhat standard to write that as the sum of the individual C's, as if we're adding curves. Are we literally adding curves? Sort of. It's a new kind of addition. And effectively, the line integral of the vector field over the entire curve, effectively by definition, is the sum of the line integrals over each curve individually. If I'm going to do that by hand, I need to parameterize these things. I can parameterize C1 with R equals T comma T, say, for T between 0 and 2. I can do these parameterizations individually, by the way. I don't have to, for example, for the parameterization of C2, I can start time at 0 again. I don't have to start it at 2. I can use a parameterization for T2 to be, if I start time at time 0, both x and y start at 2 when t is 0. X goes up by 1 to 3. T goes down by 2 to 0. What should I let t vary up to? Maybe 0 to 1 would be the simplest thing to use. So in other words, I'd do t plus 2 for x and negative 2t plus 2 for y as t varies from 0 to 1. Think about that with me. Along C2, both x and y start at 2 when t is 0. That's going to happen. When t is 1, x has gone up to 3, and y has gone down to 0. It's not, these parameterizations are not unique. This just seemed like the simplest one to pick to me. And again, I don't have to start time at 2 since the last one ended at 2. I can sort of restart time at 0. I can use any parameterization I want for each individual piece. For C3, Once again, maybe I use t goes from 0 to 1. X starts at 3 and goes down to 0. So I'd want like negative 3t plus 3 for x. And y stays at 0 the whole time. These are 3 example parameterizations that you'd do for this. You need to find r prime for each one of these to help you do the individual integrals. It's nice because they're all linear functions of t. You're going to get constant derivatives. 1, 1 there, 1, negative 2 here, and negative 3, 0. Plugging into f is not going to be so pleasant because f was slightly complicated. It's not too bad, but the vector field, capital F, is this thing here. I could plug it into Mathematica like this. I think it's a good thing to put curly braces around the x and the y so that it allows you to plug in points if you want. But its formula is just this thing here. 2, for example, let's figure out what f dot r prime is in each case. For C1, I'd plug in t comma t into f. And I would dot that with the constant vector 1, 1. I'm computing the dot product of this thing plugged into f with that constant vector 1, 1. That's going to be the integrand for this first integral over C1 as t goes from 0 to 2. Notice I did a dot product in Mathematica with a period. It's not a star. That's a dot product. I've mentioned that before, I believe. That's the function you integrate from 0 to 2. Fairly easy to do by hand. The integral over C1 equals 12. Now do the integral over C2. I've got to plug in that thing into f. T plus 2 goes in place of x. Negative 2t plus 2 goes in place of y. If you did it by hand, think about it with me. You'd have to, for example, when you square that, you got an x squared. You'd have to square t plus 2. You'd have to FOIL it. You're going to get a quadratic. That's going to get dotted with this velocity vector, 1, negative 2, to give you that expression unsimplified. Simplify it now. That's what you would integrate as t goes from 0 to 1 for the second integral, not 0 to 2. Once again, not too bad to do by hand. Giving you 21. I claim I can figure out what the answer is for this last one before even doing it. We're leading up to a drum roll here. I'm going to plug in negative 3t plus 3 comma 0 into f, dotted with negative 3, 0. Simplify. Didn't expand it. Okay, expand. Yep. Okay. I claim when I do this last integral, I claim the answer is going to be negative 33. Drum roll. There we go, negative 33. How did I know that? I knew it had to be the opposite of the sum of these two things. 12 plus 21 is 33. I knew it had to be negative 33. How did I know that? It's a special vector field, that's why. This vector field is the gradient of a function. It's a conservative vector field, which is part of the reading, part of the homework, is to understand conservative vector fields. Conservative vector fields are those vector fields that are gradients of some function. And when they are the gradient of a function, if you integrate them around some closed path, my path was a triangle, that ends where you start, the integral has to be 0. More generally, if you integrate over some other path that may not be closed from A to B, the integral of this vector field over such a path from A to B turns out to be little f of B minus little f of A. That looks a lot like the fundamental theorem of calculus, and it is. Little f is like an antiderivative for this vector field. It's got a special name. It's called a potential function in this case. That's not because it's maybe a function, maybe not. It's related to potential energy. That's why they call it a potential function. That's a special kind of vector field. You're also in the reading going to see something about a condition for the vector field being conservative related to the curl of the vector field being 0. Watch out for that in the reading as well.